Welcome back to Science Modernizers. Welcome back to this video. Today we are going to see a problem on sequences, that's recurrent sequences, and this question is an extract of the lower seat promotion examination in the Lycée Bilingue d'Application, that's Government Bilingual Practicing High School, GB PHS Yaoundé, and this was proposed by the head of department, Mr. Rins. So let's get started with the video. So the question reads, given the sequence un, where n belongs to the set of natural numbers including 0, defined by, we have u1 is equal to 5 on 2, and we have un plus 1 is equal to 3 minus n on 2 into n plus 1 times 3 minus un. Roman 1, prove that for every n in n star, un is less than 3, 5 marks. Roman 2, show that un is un plus 1 minus un is equal to n plus 2 divided by n divided by 2 into n plus 1 times 3 minus un, and hence study the monotony of un. Now Roman 3 says show that un is convergent, and the continuation we have let vn be n into 3 minus un, where n is a positive integer. Show that vn is a geometric sequence and state its common ratio. So let's proceed with the video. So we are going to begin with Roman 1. So to prove Roman 1, we are going to pass through mathematical induction. So we want to show that for every n which belongs in n star, un is less than 3. Okay, so we are going to begin by using the 3 main steps for induction to prove by mathematical induction. So we are going to prove the base case. So we are going to prove when n is equal to 1. So we can let the statement be pk, be a certain pk, or let's say pn, sorry, a certain pn. Now we want to prove for n equal 1, that is p1. Now at n equal 1, what do we have? We have u1 is equal to 5 on 2, which is given, and this in decimals is 2.5, and definitely this is less than 3. So we can say this is true for n equal to 1. So it means p1 is true. Let's say that is p1. Now the next we are going to use the induction hypothesis. So we are going to assume the induction hypothesis. We are going to assume that pk is true, that is when n is equal to k. Now when n is equal to k, we have that uk is less than 3, so we'll call this equation 1. That's the induction hypothesis. Now the next, we are now going to prove for pk plus 1. pk plus 1. Okay, now proof for pk plus 1 means we are proving for n equal to k plus 1. Now may recall the sequence was defined recurrently by un plus 1 is equal to 3. So let's recopy that. We have un plus 1 is equal to 3 minus, what do we have, n divided by 2 into n plus 1, n divided by 2 into n plus 1, all of that divided by 3 minus un. So that's it defined recurrently. So for uk plus 1, I'm simply going to replace my n by k. So this means we can have uk plus 1 will be equal to 3 minus k divided by 2 times k plus 1, all of that times 3 minus uk. Now from here we have to verify that this statement is less than 3. Now let's do some little analysis. Now the first thing we can deduce here is n belongs to n star, and so this also means that k belongs to n star, and so what does it mean? It simply implies that k is a positive number, in other words greater than 1, and if k, or let's say greater than or equal to 1, now this also implies that the ratio k divided by 2 into k plus 1 will be less than 1 for every k which belongs in the set of natural numbers. So that's the first thing we can see. And so the number 3 minus uk, from my induction hypothesis, we saw that uk is less than 3. So if uk is less than 3, it means this difference, 3 minus uk, will always be something less than 3. And so since something less than 3 can multiplies anything less than 1, then 3 minus this particular difference should definitely be less than 3. But to do this, we are going to introduce an inequality sign using the assumptions below. So I'm going to use the assumptions above. So I'm going to use this case that k divided by 2 into k plus 1 is less than 1. So this can be used. I'm going to replace that by its maximum value. So I'm going to have that uk plus 1 will be less than 3 minus 3 minus uk. So I've taken the maximum value of k divided by 2 into k plus 1. So what does this imply? It means we have that uk plus 1 is less than 3 minus 3 plus uk. And so what does this imply? It means uk plus 1 is less than uk, but uk on its own side is less than 3. So this means uk plus 1 is less than 3 as required. So we have proven that uk plus 1 is less than 3. Another way of proving that uk plus 1 is less than 3, we can say that from induction hypothesis, since uk is less than 3, one can say that using the inequality, it means that uk plus 1 will be less than, we have 3 minus k divided by 2 into k plus 1, all of these times 3 minus uk, which is 3. So we take the maximum value and we change the equality sign to the inequality sign. So 3 minus 3 gives 0, and k divided by 2 into k plus 1 still gives 0. So from here you clearly see again that uk plus 1 is less than 3, hence true for pk plus 1, that's at n equal k. Now we conclude, since is true, since pn is true for n equal 1, n equal k, and n equal to k plus 1, then it's going to be true for every n which belongs to n star. Okay, so let's take the Roman 2 part of the question. Now the Roman 2 part of the question says, show that un plus 1 minus un is equal to what is on the screen. Okay, so let's recall our definition of un plus 1. So Roman 2, so we want to show that un plus 1 minus un is equal to n plus 2 divided by 2 into n plus 1, n plus 2 divided by 2 into n plus 1 times 3 minus un. Okay, so I want to show this proof. Okay, remember that un was defined recursively by un plus 1 is equal to 3 minus n divided by 2 into n plus 1 n plus 1 times 3 minus use of n. Now if I subtract un from both sides, it means I will have un plus 1 minus un will be equal to, I will subtract it 2 from here, that will be 3 minus un. So I've subtracted un from both sides. Okay, now then I'll add the other terms, that will be minus n divided by 2 into n plus 1, all of this times 3 minus un. Now, so what do we get? This means that our un plus 1 minus un will be equal to, you see that 3 minus un and 3 minus un is common, so factor it out and keep it on one side. So what will be left here is 1 minus n divided by 2 into n plus 1, all of this will be multiplied by 3 minus un, like that. So if we simplify this, 2n plus 2, so we take LCM, here we have 2n plus 2 minus n divided by 2n plus 2 into n plus 1. This multiplies 3 minus un. Now if you simplify that, we have that 2n minus n is n plus 2 divided by 2 into n plus 1 times 3 minus un as required. So that's un plus 1 minus un. Now the next part of the question says, and hence study the monotony of un. So let's study the monotony of un. So monotony means it suffices for us to study the inequality un plus 1 minus un. If this is positive, then we are going to say that it's increasing, un is increasing, and if it's negative, we are going to say un is decreasing strictly. Now what do we have? We already have an expression of un plus 1. Un plus 1 minus un is already equal to, we have it to be n plus 2 divided by 2 into n plus 1, then times 3 minus un. Now we realize this. Now what we do is, we are simply going to use some notions on inequality here to verify the sign of this quantity to see if it is positive or negative. Remember, n is a natural number, and so since it's a natural number, it means the ratio n plus 2 will definitely be positive, and since n2 is a positive natural number, it means n plus 1 will be positive. So all this thing is positive. So the ratio of a positive quantity divided by another positive quantity will definitely be positive. So I repeat, n is a natural number excluding 0. So what we have is n plus 2 will be positive. So if you take any natural number 4 to 10 and so on and so forth, plus 2 is going to be positive, divided by 2 into n plus 2, it will still be positive. So at the end of the day, what do we realize? We see that n plus 2 divided by 2 into n plus 1 will be positive for every n which belongs to the set of natural numbers excluding 0. Now remember, we proved by induction in the first question, and we should verify that un was less than 3 by induction, which was true. And so if un is less than 3, what does this imply? This means that un minus 3 is less than 0. Now, but we are looking for 3 minus un to know the sign. So if I multiply all through by a negative sign, the sign of the inequality will be reversed. So I will have 3 minus un will now be greater than 0. In other words, positive. Now this quantity is positive and this other quantity is positive. So the product of two positive quantities will definitely be positive. So from there we can conclude that the difference un plus 1 minus un will definitely be positive. Hence the monotony makes us to understand that un is strictly increasing. So that's the monotony. Now let's go to the next question. The next part says show that un is convergent, 1 mark. So that will just be writing, because you just have to justify the fact using the convergent monotonic theorem. Now basically, what do we know? If a sequence, that's the convergent monotonic theorem, so you have to note that if a sequence is increasing and bounded above by a given value, so the supremum, and in this our case it is bounded above by 3, then it means that sequence will converge to the supremum, that's 3 itself. So we see that since this is already monotonic increasing and it is also upper bounded by 3, it means it is going to converge to 3. So that's what we are going to use to justify this. That's all. So you simply make the statement that since un is a monotonic increasing sequence and it's also bounded above, then it is convergent. That is, it converges. Now to which value is it going to converge? It's going to converge to its upper bound. Okay. now the next part says let Vn be equal to n into 3 minus un, where n is a positive integer. Show that Vn is a geometric sequence and state its common ratio. Okay, let's take Roman 4. Now what do we have? Okay, so it means we have our Vn is n into 3 minus un. Hope we are not mistaking anything. N into 3 minus un. Okay, now we have to show that Vn is a geometric sequence and state the common ratio. So in order for us to show that this is a geometric sequence, it suffices for us to show that Vn plus 1 divided by Vn is equal to some k. K can be a real number. So for it to be a GP, we are going to exclude the case of 0. So what do we have? This implies. Now let's find Vn plus 1 divided by Vn. Now we already see that Vn is n into 3 minus un. So we have Vn plus 1 will be equal to n plus 1, all of this times 3 minus un plus 1. So let's get now the ratio. Vn plus 1 all over Vn. So this will be equal to, our Vn plus 1 is n plus 1 all of this times 3 minus un plus 1 all of this divided by Vn, which is n into 3 minus un. Okay, so this implies our Vn plus 1 divided by Vn will be equal to n plus 1, okay, into 3 minus, remember what's the definition of un plus 1 recursively? So our recursive definition of un plus 1 was 3 minus n divided by 2 into n plus 1, all of that times 3 minus un. So that's what we have. Okay, now all of this will be divided by n into 3 minus un. So this implies Vn plus 1 divided by Vn will be equal to, okay, so let's simplify this. We'll have n plus 1 times, what we have here is 3 minus 3, 0. This negative and this negative becomes positive. Okay, so we have n divided by 2 into n plus 1, then times 3 minus un, all of this divided by n into 3 minus un. Now let's rewrite this in a way that cancellation will be evident. This will be, now n plus 1 times n is n into n plus 1 into 3 minus un. Now what is on the denominator? 2 into n plus 1 will multiply this denominator. So we have 2 into n plus 1 times that n into 3 minus un. Now let's do the cancellation. You see that n plus 1 cancels n plus 1, 3 minus un cancels 3 minus un, n cancels n. So all we are left with is half. So we have that Vn plus 1 all over Vn is equal to a constant, which is a half. Hence Vn is a GP as required. Now the next is find the common ratio. So what is the common ratio? The common ratio R is simply Vn plus 1 all over Vn, which is what? Half. So therefore R is equal to a half. So this brings us to the end of this video. I hope you loved the video. Do not forget to like, share and subscribe, and drop your questions in the comment box. See you in the next video.